All right, today we're going to crack a really cool code, one that's hiding in plain sight inside this simple binary tree. It's a classic coding puzzle, the kind that takes a visual structure and turns it into a single, kind of surprising number. So, let's dive right in. So, here's the central mystery. Take a look at this binary tree. It's just full of ones and zeros, right? But somehow, if you add up all the paths from the very top to the very bottom, you get the number 22. I mean, how does that even work? How do you turn a path into a number? Is there some secret formula? Well, that's exactly what we're going to figure out together. Now, the solution isn't buried in some super complex math. No, it actually all comes down to one single crucial rule. It's all about how we're supposed to read this tree. And once you get this one clue, everything else just clicks right into place. Okay, but before we get to that big rule, we got to do a quick refresher on a really key concept, the most significant bit, or MSB for short. So think about the number 100. That one out front, that's the most significant digit, right? Because it stands for hundreds, not just ones. Well, in binary, it is the exact same idea. It's just the bit all the way on the left that carries the most weight, the most value. And here it is. This is the rule. This is straight out of the problem description, and it's basically our Rosetta Stone for this whole puzzle. It tells us that every single path from the top, from the root down to a leaf, represents a binary number. And here's the kicker, the root is always the start of that number. It's always the most significant bit. That's the key right there. All right, let's put that rule into action. We're going to take a walk down the very first path and see exactly how we can build a number one step at a time. Okay, let's trace this leftmost path together. It goes 1, then 0, then 0. We start at the root, which is a 1, so our number so far is just 1. Easy enough. Now here's the trick. When we move down to the next node, that 0, we use a super simple formula. Take the number we have, multiply it by 2, and then add the value of the new node. So that's 1 times 2 plus 0, which gives us 2. Got it? Let's do it one more time. We take our current number, 2, multiply it by 2, and add the new node's value, which is another 0. So 2 times 2 plus 0 equals 4. And just like that, the path 1, 0, 0 gives us the number 4. So you might be asking, why are we multiplying by 2? What's the magic in that? Well, this is the core of the whole thing. See, in the world of binary, multiplying a number by 2 is the exact same thing as shifting all its bits one spot to the left. It's like you're shoving everything over to make space for a new digit on the end. And that action, that little shift, is what guarantees that our starting number, the root, always stays in that all-important, most significant position. Every time we go down a level, we're essentially pushing the root's value further to the left, cementing its importance. And look at this. Here's where it all comes together. On the left, you've got our step-by-step math. On the right, you see what the path 100 actually means in binary. It's also 4. So our little calculation, it's just a clever, dynamic way of converting a binary number that we read off the tree into its decimal value. The path literally is the binary number, and our simple algorithm is just the translator. Awesome. We've totally cracked one path. So now we just have to use that exact same logic for every other path that goes from the root all the way down to a leaf. And then we can finally solve the whole puzzle. And this table just lays it all out nice and neat. We already did the first one, right? The path 100 gave us 4. Now look at the next one, 101. That gives us 5. Then you've got 110, which turns into 6. And finally, the path 111 becomes 7. It's that same multiply by 2 and add logic over and over again for every single route you can take down the tree. And now for the grand finale. We just take the decimal values from all 4 of those paths, the 4, the 5, the 6, and the 7. We add them all up, and what do we get? There it is, 22. Mystery solved. Okay, so solving it by hand is one thing, and it's pretty cool. But let's just take a second to appreciate how simply and powerfully a computer can do this in an instant. This is where the real beauty of the algorithm shines through. So everything we just did, all that path tracing, all that multiplying and adding, it can all be boiled down to this one single, elegant line of code. This little formula is the engine that drives the whole process. It's a recursive function, which is just a fancy way of saying the function calls itself over and over again for each new branch, carrying the running total with it as it goes down the tree. It's just automatically applying our multiply by 2 and add rule at every step, building the number until it hits the bottom. So why is this approach just so perfect for this problem? Well, a few reasons. First, and this is the most important part, it perfectly locks in the root as the most significant bit by constantly shifting the number to the left. Second, because it's recursive, the code can explore each path all by itself without getting its wires crossed with the other paths. And finally, it knows when to stop. It has a built-in stop sign. As soon as it hits a leaf node, one with no more branches, it knows that path is done and it adds that final number to the grand total.
Now, this is a really fun puzzle, for sure. But it also points to a much bigger idea, you know? So, what's the real takeaway from all this? I think this puzzle is just a perfect example of the real elegance you find in computer science. Think about it. We took a really simple structure, a tree, and we combined it with a really simple, repeatable rule, our multiply and add algorithm. And what we got was a powerful system that could translate a visual layout into actual, meaningful data. It really shows how it's all about finding that simple, powerful core logic that can unlock something that seems really complex on the surface.
And that kind of leaves us with one final thought to chew on. We just saw a tree represent numbers, right? But what else could it be? I mean, think about a family tree, or the way an AI makes decisions, or even just the file system on your computer. It's all trees. And it really makes you wonder, doesn't it? What other huge, complex ideas are just out there, waiting to be understood and solved by mapping them onto a simple, elegant structure like this one?